Well, good morning. We have a 2.6 to work through today, so we'll get right into it. It says, at first, Optima's quilts only made square blocks for quilters, and Optima spent her time making perfect squares. Customer service representatives were trained to ask for the length of the side block, X, that was being ordered, and they would let the customer know that the area of the block would be quilted using the formula A of X equals X squared. Optima found that many customers that came into the store were making designs that required a combination of squares and rectangles. So Optima's Quilts has decided to produce several new lines of rectangular quilt blocks. Each new line is described in terms of how the rectangular block has been modified from the original square block. For example, one line of quilt blocks consists starting with the square block and then extending one side length by 5 inches and the other side length by 2 inches to form a new rectangular block. The design department knows that the area of this block can be represented by the expression A of X is equal to X plus 5 quantity times X plus 2. But they do not feel that this expression gives the customer a real sense of how much bigger the new block is. For example, how much more area it has when compared to the original square blocks. So the first one right here is, can you find a different expression to represent the area of this new rectangular block? You'll need to convince your customers that your formula is correct using a diagram. So we can go ahead and I'm actually going to do the algebraic version first of X plus 5 times X plus 2. And hopefully you're thinking to yourself right now, how do I get a different algebraic expression? Well, I can FOIL, or Tayson, you can Loeif, or whatever you call it. But you can FOIL and just do that distribution. So X times X is X squared. X times 2 is 2X, 5 times X is 5X, and 5 times 2 is 10. By looking at these like terms right here, I can go ahead and simplify this one step further by saying X squared plus 7X plus 10. Now for a diagram, I'll start with my X squared block like I normally do, and one side is extended by 2, just like that, and the other side is extended by 5. 1, 2, 4, and 5. So then we just go ahead and extend these. Now, almost. And now if we go ahead and count each of these individual spaces, we have an X squared block. We have 5 X's up here. We have 2 X's over here, and a total of 10 unit blocks right there. So if we go ahead and count them up, we've got X squared plus 7X plus 10, just like that. Here are some additional new lines of blocks that Optima's Quilts has introduced. Find 2 different algebraic expressions to represent each rectangle and illustrate with a diagram why your representations are correct. So I want you to go ahead and pause. Well, actually, in just a second, I want you to pause the video. I want to do number 2 with you, and then pause the video and go ahead and try 3, 4, and 5, and then you can come back to the video after that and check to see if you got them correct. But I'll do number 2 with you first. So it says the original block, always start there, was extended by 3 inches on one side and by 4 inches on the other. So it's almost a square, but not quite. And those blocks also extend up here into this top corner. So in terms of the side lengths, we have X plus 3 and X plus 4. So the area in terms of the side lengths is X plus 3 times X plus 4, just like that. But now for the area in terms of the area blocks, we'll just go ahead and count them up, where we've got this X squared, we have 3 X's right here, we have 4 X's up at the top, and then we have 4 times 3, or 12 unit blocks right there. So we can count those, add them all together. 4x plus 3x is 7x. And finally, we have our 12 unit blocks there. So take this opportunity now to pause the video, try to work through 3, 4, and 5, and then you can come back to the video after a couple of minutes. All right, well, hopefully you were successful. We will look at this next one, number 3, the original square block extended by 4 inches on only one side. So here we have our square block, and 1, 2, 3, 4. So it's just x plus 4. The top has no extension at all, so that side is just x. And our area could be, in terms of the side lengths, x times x plus 4. Or in terms of the area blocks, I just have an x squared here, and then I only have 4 x's right here, and I have no unit blocks. So I could just go ahead and say x squared plus 4x. Now something you'll also start to notice is if I look at these terms right up above, if I were to distribute that x through, I would get x squared and 4x. So that's just something to be aware of, that we could look at these algebraically as well. All right, number 4, the original square block was extended by 5 inches on each side. So the other one was only extended by 4 on one side, and now we've got 5 on each side. I'm going to go ahead and, wow, those all look like x squares. Tricky. They are not, though, because they are 5 individual blocks, and I'm going to go ahead and draw these all in. 1, 2, 3, 4, 5. 4 lines, 5 squares, or rectangles. 1, 2, 3, 4, 5. Again, 4 lines, but 5 rectangles. So I have x by x, and then plus 5, plus 5. So 5 x's on either side. So in terms of the side lengths, though, it's x plus 5 times x plus 5. Now at this point, you should see that's the same thing. If it's the same thing, what is something times itself? Well, it's just that thing squared. So x plus 5, quantity squared. That's an easier, simpler way to write that. Now, some of you have looked at this as though, okay, x squared, if I want to do this algebraically, I can just go x squared and 5 squared, right? Woo! Not the case, because look at what we started with right over here. We start with 2 binomials, so instead of having just, you cannot distribute this square across addition. You can only distribute those exponents across multiplication. So instead of just distributing that through and calling it quits, what we actually have to do if we wanted to do it algebraically would be FOIL or LOEIF. But in this case, we're actually just counting these, right? We've got x squareds, 5x, 5x, and then we have 5 times 5, which is 25 unit blocks. So we could even see the area is x squared plus 10x plus 25. And if I just were to do this over here, I would only get x squared plus 25, and that leaves out this third term in the trinomial. This is the incorrect answer, so we cannot do just that, okay? That's the importance of foiling. And here's an example as to why it matters, right? Okay, now, number 5, the original square block was extended by 2 inches on one side and 6 inches on the other. So as you were checking through these, 2 inches, let's say it's 2 inches on the top, and then it'll be 6 inches over here. So I'll go ahead and I'll extend this out. 1, 2, 3, 4, 5 lines and 6 blocks. So now I've got a side that's x plus 6 and a side that's x plus 2. So when I find the area in terms of side lengths, it is x plus 2 times x plus 6. When I find the area in terms of area blocks, it's x squared plus 2x on the top and 6x on the right side. So it'll be plus 8x plus I have 6 times 2, which is 12 unit blocks. Okay, so there's number 5. Now we've got some different stuff. We're going to go the other direction for these next several problems. And it says customers start ordering custom-made block designs by requesting how much additional area they'll want beyond the original area of x squared. Once an order is taken for a certain type of block, customer service needs to have specific instructions on how to make the new design for the manufacturing team. The instructions need to explain how to extend the sides of a square block to create the new line of rectangular blocks. The customer service department has placed the following orders on your desk. For each, describe how to make the new blocks by extending the sides of the square block, that's in words, with an initial side length of x. Your instructions should include 1, a diagram, 2, written description, and 3, an algebraic description as well. For the area, of the rectangles using the expressions representing the lengths of the sides. So in a similar fashion, I want to do this first one with you, and then I'll give you an opportunity to pause, try working through them on your own, come back, look at your process, and see if you were successful. So this first one, we can kind of see that there are 5x blocks on one side and 3x blocks on another. So as we're looking at our diagram, we could say, okay, I see how this thing is separating out. So I've got 3x's on one side, 2, 3, and I've got 5x's on the top. So I'll go ahead and draw those in. 1, 2, 3, 4. Those are not symmetrical, but they exist. All right. So x plus 5 and x plus 3. You see how these 3 are arranged straight over there. These 5 are arranged straight over there. Now, when I combine those two and multiply for those unit blocks, I also see that I get 15 and a single x squared block. Sorry, there was a little glitch in the system, so I had to redraw that block. Those 5x's are a little bit nicer now, actually, so happy accident. So we can use the previous written descriptions as kind of a guide for us, where they said that the square block should be extended by this amount on one side and this amount on another side. So I'll say the square block extended, well, how many was extended by? It was extended by 3 inches on one side and by 5 inches on the other side. So I know it's a little taxing to write all those words down, but it will be good. So now let's go ahead and write the algebraic description. So they've got one style, the area in terms of the area blocks up here, but now we need to write the area in terms of the side lengths. So our side lengths are x plus 3 and x plus 5. So there's the formula for the area. If you want to get really specific in function notation, you could say a of x is equal to x plus 3 times x plus 5. Okay, and actually I am just going to do that one with you, and then I will come back and have the answers up in just a little bit, and you can see if you got those correct. Well, now it's time to check, so we'll start with this one. We've got x plus 4 and x plus 6, so we should have our original x squared block, add 4 on one side, and 6 on the other. It's getting a little wavy, but it works. So plus 6, plus 4, x and x. So there we have it. If you look up here, 6 times 4 is actually 24. So we are all good to go there. Let's look at the next thing we need. We've got our diagram. Now we need a written description. So I will say this out loud and you guys can go ahead and write it down. But this written description should be this square block extended by 4 inches on one side and by 6 inches on the other side. So you can go ahead and have that written description out on your lesson. And finally, the algebraic description will be, in terms of the side lengths, x plus 4 times x plus 6. Okay? Now the next one, we have 9x and 2. I think I'm better at estimating these horizontally than vertically, so I'm going to go ahead and put that 9 out here. And we do need the diagram for this, so I'll extend all this. Let's see if we can't get 8 lines and 9 rectangles. So there's 1, 2, 3, 4, 5, 6, 7, 8. For some reason, I'm just better at it horizontally on those, or vertical lines there. On the horizontal length. So our side length there is x plus 9 and x plus 2, which when we multiply 9 and 2 together, we get total of 18, which is excellent. So again, I will kind of dictate that written description, and then you can write that down. You can scribe that down, but it should be the original x, or the original square block extended by 9 inches on one side and by 2 inches on the other. And finally, the area in terms of side lengths, x plus 2 times x plus 9. I said that backwards, but there you have it. X plus 9, x plus 2. Remember, that's the same thing as x plus 2 times x plus 9. When you have multiplication like that, you can flip the whole term, one term for the other. Doesn't matter the order, which is kind of nice. Okay, the final one, the x squared block. We've got 5 x's on one side and one single, a lone x on the top. So we'll go ahead and say x plus 1, put our 5 in over here, 2, 3, 4, and x plus 5. So we have our side lengths there, and when you multiply 5 times 1, you get 5. So I will go ahead and dictate this one now too for you to scribe down. This is the square block with 1 inch added on one side and 5 inches added on the other. If you'd like to be a little bit more specific, you could also come back up here and say extended by 1 inch on the one side and 5 inches on the other. It's up to you. Also, in terms of the side lengths, we have x plus 1 times x plus 5. We just take both of those side lengths and multiply them together. All right. Now we'll move on to some of the orders are written in an even more simplified algebraic code. We need to figure out what these entries mean by finding the sides of the rectangles that have this area. Use the sides of the rectangle to write equivalent expressions for the area. So now, what you'll notice up here is that what we kind of had was these additions were what we're multiplying to our unit blocks, right? So 3 and 5 multiplied to 15. 4 and 6 multiplied to 24. Now, in this section, they had those split up for us. But now we're going to have to find the terms that multiply to this last term, c, as we would call it in standard quadratic form, and that add to the center term, the simplified center term of these questions 10 and 11 and so on, of b, as we would call it. So they need to multiply to the last term and add to the second term. So as I'm thinking of factors of 10 that might add to 11, I think the factors of 10 are 2 and 5, which would add to 7, or the factors of 10 are also 10 and 1, and those actually do add to 11. So what we can actually do is we could say, okay, I've got this block here, the x squared block, and I'm going to have it added by 1 on one side, and I'm going to have it added by 10 on the other side. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So x plus 10, x plus 1, and you can actually count up there if you want to, or just note that 10 times 1 is 10 unit blocks. But I have 10x blocks right here, and I have 1x block up here, which gives me the sum of 11x's. So the area in terms of side length is going to be x plus 1 times x plus 10. So there's the area for that one. This next one, I even already said it because I said the factors of 10 are both 10 and 1, but also 5 and 2. So this next block, I could actually look at 5 and 2 because 5 and 2 add to 7. So as I'm looking at that diagram, I'll have x with 5 on one side and just 2 on the top side. 2, 3, 4, 5. And you notice again that this plus 5 and plus 2, they multiply to the last c term, but we have 5x's and 2x's, which add to 7x, or that b term. So the area in terms of the side lengths here would be x plus 2 times x plus 5. Okay, I know it's going to take some discipline, but I want you guys to work on these next several by yourselves. And this time, I am only going to come back together to do number 16 with you. So you will be on your own or work with your classmates to get 12 through 15, but I'll come back together and do number 16 with you. So go ahead and take some work time and do that. Alrighty, it's time for number 16. We have several factors of 12, as you well know by now. You can even see in 14, 15, and 16 all these different options, 7x, 8x, or 13x. Now in 16, the factors of 12 that add to 13 would be 12 and 1. Other factor options are 3 and 4 or 6 and 2. But in this case, we'll do 12 and 1. So we will have our original x block. We'll have 12 on one side and 1 on the other. And we'll go ahead and make all these. 1, 2, 3, 4, 5, 6, 7, 8. Gonna just keep extending that. 9, 10, 11, 12 blocks. So x plus 12 and x plus 1. So area in terms of side lengths, x plus 1 times x plus 12. And all of these you could verify by algebraically foiling or loafing. So finally, the last two questions were here before our RSG. Question 17 says, what relationship or patterns do you notice when you find the sides of the rectangle for a given area of this type? Now what we should have noticed is, let's say that this is in the standard form of ax squared plus bx plus c, that's the standard quadratic form. What we should have noticed is that the factors of c will add to b. Okay, that's how we have to we have to factor this. So we would say things that multiply to c add to b. That's kind of another way we could say it. So the factors of c add to b. Okay, or we're looking for two numbers that multiply to c, or as Sammy might say, but is trying to quit, say times to c, and add to b. There are several ways to say that, right? They times to c and add to b. They multiply to c and add to b. You could also say their product is c and their sum is b. Those are different options. Now a customer called and asked for a rectangle with the area given by x squared plus 7x plus 9. And they are asking if we could factor that. Now the service representative said they could not make that rectangle. Now do you agree or disagree? I want you to try this for about a minute or two and discuss with your classmates real fast, and then come back to this video and see the answer. See if you are correct in your hypothesis. Okay, so what we should come back to see is that what we just said in 17 is that there need to be factors of c that add to b, right? And the only factors of this c, 9, would be 9 and 1 or 3 and 3. Now, neither of those options will add up to the number 7. So we cannot say that those add up to 7. How can we tell if a rectangle can be constructed, a perfect rectangle? Is we would have to say there have to be some factors of c that add to b. That's how you can tell. So you can write that down for that final question. All right, go ahead and get after lesson 2.6. If you have any questions, I will be back on Wednesday to tackle those with you.